Problem 45. Use the exponential decay model, A equals to A0 e to kt, to answer the following question. The half-life of thorium-229 is 7,340 years. How long will it take for a sample of the substance to decay to 20% of the original amount? Round k to 6 decimal places and the number of years to 1 decimal place. Well, here's the idea. This is exponential decay, so we're dealing with a function whose graph looks like this. I mean, before time equals 0, I'm drawing it dashed. So this is the mass, and the vertical axis represents the mass, and the horizontal axis represents the time in years, and mass in grams, or, well, it's not specified, and it doesn't matter for this question. And depending on the two parameters, A0 and K, you may have different graphs. Maybe you started with a lot of mass at time 0, but the half-life is very short, so the mass decays very quickly, like green. Or you started with less mass and it decays a little slower, a little more stable. So to figure out which kind of decay function you have, you need to specify two numbers, and that A0 and that K. And A0 controls where you start, and K controls how fast the decay occurs. Do you have something like green or something like black? So 2 points will be enough to 2 pieces of information will be enough to answer it, to find the model. The thing is, for this particular question, we don't need the initial mass because the question is asked in relative terms. In general, you need at least 2 points, and if you give me 2 points on the graph of a decay function, that's going to determine those two numbers, 2 pieces of information. I need 1 point to figure out K, and I have it. It's in the half-life definition of the half-life. So what are we given? In 7,340 years, on one hand, let me write my model, P to KT, A0 is the initial mass, and K is the decay rate. On one hand, I have half of the initial mass, and it is the initial mass because when you plug in K equals to 0, then E to 0 becomes 1, right? No matter what K is. So A0 times 1 is A0. So at time t equals 0, you get A0. So after 7,340 years, you have half of the initial mass. That's the definition of half-life. And on the other hand, what the model gives us e to the power, I don't know what K is, 7,340 years. I just plug in t into my model. So if I bring the rightmost side and leftmost side together, and I'll maybe arrange the power nicer, rearrange it, I get this equation. One important thing is this equation doesn't, well, A0 is on both sides. I can divide it, both sides by A0, and this condition is independent of A0. Which brings me to 1 over 2 equals to e to 7,340 times k. Now I want to solve for k. How do I do it? I have to bring k down on the ground. And to do that, I'm going to use the inverse function of the exponentiation. The exponential function, I take ln of both sides. On left, I will have ln 1 over 2. On the right side, I will have ln of e to the power 7,340 times k. But here's the thing, ln of e to anything is that anything, because ln computes what's the power you need to raise e to get what's inside. Well, what's inside is e to that power. So the answer is in the riddle. That's what ln and e being inverses of each other means. So I end up getting 7,340k and ln 1 over 2. And from here, I can figure out what k is easily. And this number, now this here, I'm going to need my calculator. Let me bring a calculator. 1 over 2. I take ln of it, and I divide it by 7,340. So it's going to be a number like negative 0. Oh, it's gone. Maybe I'll just take a screen cap. It's this number, right? The question says how many decimals? 6 decimal places. So 1, 2, 3, 4, 5, 6. When I round it, I get negative 0.000094. That's what k is. And then that's part 1. And part 2 is how long will it take for a sample of the substance to decay to 20% of its original mass? So I don't know that time. I'm going to denote it by t. And on one hand, I want 20% of my initial mass. 20% is the same thing as 1 over 5. So I'm going to write A0 over 5. This is what I want. On the other hand, what my model gives me, is minus A0 times e to minus 0.000094 times whatever that t is, right? I need to solve for t. And again, I'm going to get if I put the leftmost and rightmost sides, I get this equation in t this time. And again, it doesn't matter how much mass do you start with. So I can divide it by A0, and A0s disappear from both sides. Then I take ln of both sides, just like the first part. ln 1 over 5 equals to ln of e to minus 0.1234094 t. And ln and e are inverses of each other. Very similar of what happened earlier. And then I divide both sides by the coefficient of t. This is a linear equation in t, right? ln 1 over 5 divided by negative 0.000094. And then I take my calculator again, and 1 over 5 ln of 1 over 5, and I divide by negative 0.123494, and I get this number, and the question said I want 1 decimal. Okay, I'm going to keep 2 decimals, and I'm going to round to a single decimal. And one useful sanity check I would recommend is use the definition of half-life and do some jumps. So if you wait for 7,340 years, you will get half of the initial amount. If you wait another 7,340 years, that would be something like 15,000 years. You get a quarter of the initial mass, half of what happened. Every time you move, wait for a half-life, you get half of the mass. And then if I wait even more, one more half-life. So I'm just going to write here. Well, what do I get? Oh, 0, 2, 0, 2, 2, something like that. Maybe I'm making an error. Addition error. I added another 7,340 years. Well, 22,000-ish years. I get 8 of the mass. What do I want? I want 1/5 of the mass. So does my answer fall into the right range of numbers? It kind of does, right? It's somewhere here. And that my answer seems to make sense. So I go to the answer key and check it real quick. This is a quick way to check if your answer is correct. Just do jumps in half-life, and very roughly it will tell you how much material you still have. And that's all I want to say about this question.